So last time we looked at an example for rounding error. And I want to finish up this little section with an example of our propagated error. And as soon as we get through this first chapter, we get to the real fun, which is actually doing some stuff. Okay, so we're going to use our X true. So X true is 0.1234, and our X approximate is 0.12 and our Y true is equal to 0.5673, and our Y approximate is 0.567. Okay, so our relative error in X approximate turns out to be X true minus X approximate over X true. And that number turns out to be 0.00324 1491. Then our relative error in Y approximate is going to be Y true minus Y approximate over Y true. And that turns out to be 0.000528821. Okay, so let's look at some errors here. So let's do first, what is the relative error if you take and you multiply X approximate, Y approximate? So really I want X true times Y true, but instead I want, I get X approximate, Y approximate. Well, we proved that this is very close to the relative error in the X approximate plus the relative error in Y approximate. And so this turns out to be 0.003770312. And if we compute X approximate, Y approximate, that gives us 0.069741. And the true error, the relative error in X approximate, if we actually, X approximate, Y approximate, if we actually do the calculation, turns out to be 0.003768598. And those two are very close. Okay, so you can see this number is if you just take the sum of the relative errors in X approximate and Y approximate, And this one is if you actually take and you compute the relative error in the product of those two. Okay, so you can see that what we get as an approximation for doing that is very, very close. Okay, let's do B. What's the relative error if I take X approximate and I divide by Y approximate? Well, we said that that's very close to the relative error of X approximate minus the relative error of Y approximate. And that number is 0.00271267. Okay. If I take X approximate and I divide by Y approximate, I actually get 0.216931,217. And if I actually compute the true relative error in X approximate divided by Y approximate, not what I expect to get based on our theory, this turns out to be 0.002714106. So you can see, again, they are actually very, very close. Okay. Now, we also said we didn't really know what would happen if we looked at the sum and the difference. So here is X approximate plus Y approximate, and that turns out to be 0.69. And the relative error in X approximate plus Y approximate turns out to be 0.0010113 and some other stuff. Okay, so we didn't have any way of figuring out prior to how we could actually calculate that. We just didn't know how we would actually calculate it. And D, if I take X approximate and subtract Y approximate, I get negative 0.444. And the relative error of X approximate minus Y approximate turns out to be negative. Well, it shouldn't be negative. The relative error should actually be absolute value. Some books don't use absolute value. I like to use absolute value. So I'm going to go ahead and use absolute as an absolute value. So this is 0.0002253. And again, we could have never predicted it, but we can actually compute it. Okay. Okay, so let's talk about loss of significance of error. Okay, All right, so here's my example. So I want to solve x squared minus 26x plus 1 is equal to 0. And I'll use the quadratic formula, and I get x is equal to 26 plus or minus the square root of 26 squared minus 4. So you can actually see that that number is very, very close, all over 2. So this is 13 plus or minus the square root of 168. Now, we already know that 13 squared is 169, okay? So the square root of 168 is very close to 13, all right? So we get our first solution, x true number 1, turns out to be 13 plus the square root of 168. And that's 25.96148. And then our second solution is 13 minus square root of 168. And it is 0.03851. Okay, I wrote the wrong answer. 3851.860. Okay, there we go. All right, so now let's say we use a 5-digit machine. And so it calculates the square root of 168 as 12.961. Okay, so that's what it uses. Then the approximate solution for the first root turns out to be 25.961. And then the approximate solution for the second root turns out to be, oh, I apologize. This is 13 plus 12.961. So it turns out to be 25.961. And this one becomes 13 minus 12.961, and that becomes 0.039. All right, so let's look at the error. So if I look at the absolute value of the error in XA, the approximate to the first root, if I subtract it, it turns out to be 0.0005. And I can look at the absolute value of the error in the approximate to the second root, and it also comes out to be 0.0005. But here's the big deal. Let's look at the relative error in the approximation of the first root. Again, we know relative error is if we take the true error and divide by the actual root. So that means we're going to take the true value, we're going to take the relative error, which is 0.0005, and then we're going to divide by 25.961. And this turns out to be 1.85 times 10 to the minus 5. Okay. Let's look at the relative error in the approximation to the second root. So we're going to take 0.0005 and we're going to divide by 0.039. And we end up with 1.25 times 10 to the minus 2. And that is huge. Okay. So this relative error is large because digits were lost in the subtraction. So let's go back. When I computed the true value, we got 0.0385180. Okay. But notice what happens when we do the subtraction, well, the addition versus the subtraction. In the addition, we end up with still 5 digits, which I could write as 2.59. You know, I could write this as 2.5961 times 10 to the first power. Okay. But what happens is when we do the subtraction, we actually lose a whole lot of information. So we don't have 5 digits. We only have 2 digits. Okay, we have 3.9 times 10 to the negative 2. So the difference between having 5 digits and 2 digits causes us to have a large relative error. So here's how we can cure that. All right. So for the X true, instead, so here's the cure. Instead, for the X true, where we had 13 minus the square root of 168, and we were using 5-digit arithmetic, and that only allowed us 2 digits as remainder. Let's rationalize it with 13 plus the square root of 168 divided by 13 plus the square root of 168. So that ends up giving us 1 divided by 13 plus the square root of 168. But this now gives us 1 divided by 25.961. So now when we do 1 divided by that number, notice we're still carrying 5 digits. So now when we do the relative error in the second approximation, well, the absolute error, the absolute value of the error in the approximation to the second root, we're now going to get 3.97 times 10 to the negative 7. And so therefore our relative error, or the absolute value of our relative error, this now becomes 1.03 times 10 to the minus 5. So look at the calculation. So here the loss of significance was due to the form of the calculation, but not to the errors in the data of the computation. All right, so it wasn't how it was computed. It was basically how we chose to keep it inside the computer. Okay. Now I want to look at propagation of errors Okay, so these basically have the same type of problem. Okay, so let's say we have function of x true minus however we compute the function of x approximated. Okay, so this is the true value. And then this is the value actually computed. Okay, so we're going to do the same thing we did before. So now this is f of x true minus f of x approximate. So this is the propagated error. And then we're going to have our computer error in evaluating the function. So we have f of the approximate value minus f hat of the approximate value. And so this is the computer error in evaluating f of x approximate. Okay, so let's just do a brief example, Taylor series on propagated error. So we know we're trying to do f of x true minus f of x approximate. So that's what we want to calculate. But we know that f of x true is f of x approximated plus f prime of x approximated times x true minus x approximated plus f double prime of x approximated over 2 factorial. So this is just a Taylor series times x true minus x approximated squared plus, and I can keep going, f triple derivative of x approximated over 3 factorial times x true minus x approximated cubed. Okay. So then that says to me, really a lot of our problem is going to determine whether or not x approximated is close to x true. So that's first. So this here assumes, let me call this star. So star assumes that x true and x approximate are close. And it also assumes that the derivative at x approximate does not vary greatly between x true and x approximate. That's what makes the Taylor series work. So in other words, we get f of x true minus f of x approximate is approximately f prime of x approximate times x true minus x approximate. In other words, that's how we do our derivative. So here's an example. So given x true is equal to 2.5 with an error that we're calling E true is equal to 0.01. Estimate the resulting error in the function f of x is equal to x cubed. Okay, so we get the absolute value of f of x true minus f of x approximate. That's going to be approximately 3 times 2.5 I have a mistake in here. And I have to figure out what it is. I'm trying to think, where did I use x cubed? So I bought 3, so the derivative is 3x squared. F prime of x is 3x squared. Okay, let me check this calculation first on my calculator, because what I have in my notes is not agreeing with what's in my head. Okay, yep, this should be squared. I'm missing a squared in my notes. So, okay. So here I'm just using x true right now, because it's going to be, yeah, it would be the same. Okay. All right, so f of 2.5 is 15.625 plus or minus 0.1875. So I get that 15.43 is less than or equal to f of x true, which is less than or equal to 15.8125. And so here it is. So if XA turns out to be 2.49, then f of x approximate turns out to be the 15.4375. And if f of XA turns out to be 2.51, you find out that f of x approximate is 15.8125. I think I'm going to skip this example. I can go back and fill that in if I decide to add another example. So that was E. Yes. Now, nesting is actually very cool. All right. So the reason why nesting is so cool is because let's suppose I'm looking at f of x. Is equal to x cubed minus 6x squared plus 3x minus 0.149. X true is 4.71. and I want to use 3-digit rounding. Then when I do, so here's the problem. When I try to compute f of 4.71, I have to do 4.71 times 4.71 3-digit round. Then take that number and multiply it by 4.71 and 3-digit round again. And then I'm going to have 6 times 4.71, again, 3-digit round. Multiply it by 4.71 and do it again. You guys get the gist. Okay. But nesting of polynomials makes it so that we're able to maintain or keep more information. So here is a nested polynomial. So let's consider Pn of x, which is a naught plus a1x plus a2x squared all the way up to an x to the n. So this now has n additions and 2n minus 1 multiplications. So each time I do one of those operations, I have to 3-digit round. Okay? Each time I do that, I 3-digit round. So now let's let Pn of x so now this is a really interesting way to write this as a naught plus x times a1 plus x times a2 plus x all the way down to x times an minus 1 plus an, I think, x. Okay. So now we have n additions and n multiplications. Can you see how many times we had to round and lose information in the first calculation? So this would be, we would have f of x equaling x cubed minus 6x squared plus 3x minus 0.149 would equal negative 0.149 plus x times 3 plus, that would be minus, let's see, plus x plus 3, plus x times negative 6 plus x. I think that's right. I have this x times that x. Right, I think that's it. 1, 2, 3, 4. Okay, so now I have negative 6 plus x. When I multiply that by x, that gives me negative 6x plus x squared. And then I'm going to multiply that by x. So that'll give me negative 6x squared plus x cubed. And then I still get the 3x. Okay, so now I will compute negative 6 plus x. Then I will do 3-digit rounding. Multiply that by x and do 3-digit rounding. Add 3 and do 3-digit rounding. Multiply that by x and do 3-digit rounding. And then subtract off 0.149 and do 3-digit rounding, and I'm done. Okay, any questions about that? Okay. Okay. All right, so let's look at algorithms and convergence. So I need you two guys to come off of, I need to see you guys for a second. Okay, so Kayla and Yibing, what computer languages are you guys both planning on using? MATLAB?
Yes, I was.
Yeah, for me, using MATLAB.
Okay, and Kayla, MATLAB as well?
Yes.
Wonderful. Okay. Okay. So we want to talk a little bit just about some simple algorithms. Okay, some simple algorithms. Okay. So the first algorithm we want to do is we want to compute the sum I equals 1 to n of a group of numbers. Okay. And so we're going to assume that we either know these numbers or we're going to read them in. Okay. So the input for our algorithm, what must be known we have to know n. And we're either going to store these numbers in an array. Okay, so maybe we have an array that is n by 1. Okay, where array at I is equal to x at I. All right. So the first thing we need to do is we're going to create a sum. And so we're going to keep adding on to the sum. But in order to do so, we need to start the sum at 0 and then each time add a number. Okay. So the first thing we're going to do is we're going to assign this. So we're assuming that we already know we put these numbers into an array, we read them in, we calculated them. It could be however we want them to be in there. Okay. So the first thing we're going to do is we're going to let sum equals 0. Now, I guess you guys remember in MATLAB, if you don't end it with a semicolon, it's going to print it out. Okay, so then we're going to do for, you know what? I tell you right now, I've been coding in MATLAB and I've been coding in Java. And when I go to write them down, I get confused. So I think that's right. Yeah, for I equal okay. So for I equal 1 to n, reduce sum is going to take whatever the sum was, add to it array at I. And then we'll just end. And then you can output sum. Okay. That's how that, then we're done. Any questions? I think you ladies both know how to code, am I correct?
Yes.
Okay, so I'll do another brief one. So let's consider the nth Taylor polynomial for the sine of x. Actually, let's do, which one is even? Cosine is even. Cosine is not even, sine is even. Okay. Sum I equals 0 to n of -1 to the n x to the 2n divided by 2n factorial. Okay. So we have this one thing that we need to deal with. So the first thing we need to deal with is that MATLAB does not start with a 0th entry. Okay, so with MATLAB, MATLAB does not have a 0th entry to an array. Nor does it know zero factorial. Okay, so the one thing I would do with this one is I would let, okay, I have I's and N's in here, so there's something I got to change. I'm going to change this to an N. Actually, why don't I change that to a K? So what I will do is I will pull off the first entry. And write this as the sign of X is going to be this, is take out the first one, which is X, plus the sum, K equals 1 to N of -1 to the K, X to the 2K over 2K factorial. So any ideas about how I'm going to do this if I'm going to code this problem? What we're going to need as input I'm going to need to know the X I'm evaluating this at. I'm also going to need to know N because I need to know how many iterations of this I'm going to do. So once I know that X is a certain value, X is given, I can start off by letting the first term, instead of letting here, where I let the first one be the first element in the array, I'm going to let sum, where I started here, sum was 0. I'm now going to let sum be just plain the value of X. And the more difficult part is to try to figure out how to compute 2K factorial. Okay. All right, because K factorial is easy. So we would start off with would equal 1. And then we could do 4. So if I want to do K equals, let's see. I would let factorial just equal I times factorial. And then end. All right, so how do you walk the algorithm? You walk the algorithm because we would say if K, we want to start off with factorial equal to 1. So basically, if it's 1 factorial, that's all we get. But 2 factorial, I would be 2, and then it would be 1 times 2, and then that would be 2 factorial. But if K is 3, then we would have 3 would then be multiplying the 3 times the 2 that we already got, which would give us 3 times 2, and then we would come back around. So in order to do this each time, we would multiply by the one before, and then that would give us the factorial. Now, what happens with 2K factorial? What's the difference? Hello?
For 2k factorial, so it's not a consecutive number from 1, 2, 3, 4, 5, but 2, 4, 6, 8.
Okay, that's correct. Okay, so we're going to, so you will have to actually compute, you can either do a running sum or you can compute the entire factorial each time. Okay, so we'll have, so for 2 factorial, we'll have 2 times 1, but then we'll have 4 factorial, which will be 4 times 3 times 2 times 1. 6 factorial will be 6 times 5 times the 4 factorial. And then 8 factorial will be 8 times 7 times 6 factorial. Okay, so any ideas how to write that now? Okay, well, first off, when you do a loop and you want it to count by more than 1, you want it to count by 2s. So to do a loop, you would do 4, I equal 1 to n by 2. So actually, that's not what I want, though. I still wanted to do 1, 2, 3. I wanted to go 1 through n. Yes, I wanted to go 1 through n. So that's not going to work. That's not what I want. I still wanted to do 1 through n, but I wanted to do 2n factorial. So the first one, when I is 1, I'll do 2 factorial. When I is 2, I will do 4 factorial. Okay, that's exactly right. Okay. Jeez, I'm out of time already. Okay, I'm almost out of time. Okay, so other thing is we have to deal with the -1 to the n. Okay. So let's create something called sine. And let's start sine off as 1. Okay. So now we have 4. I equal to, we took off the 0 of terms, so now we only have to go 1 through n. Okay. So the first thing we're going to do is we're going to let sine be -1 times sine. So now when I is 1, sine will be -1. When I is 2, it'll now multiply by a -1 again and become positive. Okay, so we're going to alternate our sign. Then we have to calculate our factorial. So let's call K2. Oh, actually, I'm going to use K because that's what I used before. Okay, so 2K is 2 times K. All right, so now I know K, and now I know 2K. So now it's going to be easy for me to evaluate X to the 2K, because now I know what 2K is. It's going to be easy for me to evaluate the -1 to the K, because now I know the sign. So now what I need to compute is 2K factorial. And I need to let factorial equal 1. Okay, so in order to compute the 2K factorial, then we're going to have to take and compute 2K factorial will be 2K minus 1 times factorial. So now we know what the factorial is. And so now we can add the sum. So we can add to the sum. So now we're going to get sum is going to equal, well, we're going to take the sine. We're going to multiply it by our X to the 2K. And then we're going to divide that by factorial. And then we're going to end. And then our output will be sum. And that will be our approximation to the sign of any X. Okay, so the difficult part for this piece was finding how to do 2K factorial. Any questions? Now, here's the thing about this problem. We already know from theory that the sine of x, actually, which is equal to the sum k equals 0 to infinity of -1 to the k, x to the 2k over 2k factorial converges for the absolute value of x less than 1. So what we should see is we should see a small amount of error whenever we do this. Okay, with each, as for each n, you should see a small amount of error between the true solution and the approximated solution. Okay, and we expect to get a small amount of error. All right. So what we consider here, that's not what I want. Is we can find the error in the 0th calculation. Okay. Then the error, so the error in the first calculation, I should say, I'll have to, okay, I'm out of time. All right, I'll have to pick up here. But hopefully you guys understand